So this is where we ended last time. We had this fun little frequency table, right? And we referred to this as a probability distribution, right? So you've got the empirical probability on the right-hand side. You've got the frequency right here. And then you've got the individual items right here. And so we're going to go through an example. And in this example, we are going to pull it straight from the PowerPoint. Oops, I'm going to do this right over here. And then I'm going to put this right here. Okay, so in this PowerPoint, we've got here. We've got individuals who visit Waco. Okay, so I'm going to come over here and I'm going to make a box of every single person that visits Waco. Does that sound good? So does that look like a good box? You're like, sure, whatever. So I'm going to build this box and I'm going to put a thick outline. And should I make it a color, just like a gray? Okay, so what's the probability of being in that gray box?
1.
People visiting Waco. P equals 1. Okay, the probability equals 1. Now, we have two more boxes. Okay, we've got this box right here, and this is the probability of an individual visiting the silos. Okay, they're blue, right? That's what they do. They do blue. Okay, and then right here is the probability, so we're going to put right here, you've got people who visit the silos, and then you've got people who come here, and we're going to make this like that. We're going to make this green. Why am I making this green? They are visiting Baylor. And the cool thing is this is probably a lot higher this year than what it's been in the past because Baylor is doing epically well at pretty much everything right now, which makes me excited. So this is the probability of them visiting Baylor. This is the probability of them visiting the silos. And what is this right here? What color should we make this? Should we want to make this like, that looks good, right? What is this referred to as?
Joint.
The joint P of visiting both. Okay? So, right over here, we've got the probability of them visiting the silos. We surveyed a total of 120 people. Okay? Of those 120 people, we surveyed 200 people. Of those 200 people, 120 of them said that they visited the silos. Okay, so what is the probability of them visiting the silos, them coming to Waco and them visiting the silos? If we surveyed 200 people and 120 of them said that they visited the silos. What is it? 0.6. So the probability of them visiting the silos is going to equal 0.6. Okay. What is the probability of them visiting Baylor? We surveyed 200 people and 100 of them said that they visited Baylor. 0.5. So the probability of them visiting Baylor is 0.5. Now we're going to assume that these two events are completely independent. Okay, in other words, one does not impact the other. So if one does not impact the other, so P equals 0.5. If one does not impact the other, what is the probability of them visiting both the silos and Baylor? 0.3. And the reason why, all that you've got to do is if they are completely independent, if you want to know the probability of them doing both, all that you have to do is multiply them together. So the probability of them doing both is going to equal P equals you said 0.3?
Yes, sir.
0.3. So that's the probability of both. Okay, so we've got the probability of them visiting the silos, the probability of them visiting Baylor, and the probability of them visiting both the silos and Baylor. So in other words, what we have right here is what is the probability, we're going to go right here. What is the probability of them visiting either the silos or Baylor? How do we do this? We add them together. So we've got 0.6 plus 0.5 plus 0.3. What does that give us? Gives us way more than what we need, right?
Yeah.
Okay. So
You subtract the 30 so it doesn't get, or the 0.3 so it doesn't get
exactly. So we add the probability of them visiting the silos, which is 0.6, and then we also add the probability of them visiting Baylor, which is 0.5. And then we subtract the probability of them visiting both. And the reason why is because this 0.3 is inside of both of these, and we don't want to count it twice.
And that's to find who's going to visit.
Either the silos or Baylor. So in other words, they could visit both, they could visit one, or they could visit the other, but they're going to visit at least one of those. Okay, so we do equals this, the probability of them visiting the silos, plus the probability of them visiting Baylor, minus the probability of them visiting both, which gives you 0.8. Okay, so we've got silos, Baylor, both, either.
And that's the rule for that. It's called the general rule of addition.
The general rule of addition, precisely. Now, what is the, yes?
I was gonna say, if it was drawn to scale, could you just add up the boxes of both and then divide it by the total?
Theoretically, yes, but I did not draw it to scale because,
Yeah.
yeah. So what is the probability of them visiting neither? 0.2. So this giant gray area, P equals 0.2. Probability of them visiting neither. I don't know what you would do. I guess they went to the Waco, that place with the mammoths. They didn't come here. So, which, I don't know, can you consider that part of Baylor? Because that is there because of Baylor. It's associated. So they still went to Baylor. They just said that they didn't. They didn't realize that they were at Baylor. We own Waco. No. So that's the probability of them visiting either. Now, so I showed you this really cool thing there. Now, you guys are going to be doing the exact same thing. We're coming right in here, and we determined the empirical probability right here, and the classical probabilities right here. Yes?
What would be the probability of the people in that last example visiting either the silos or Baylor?
The probability of them visiting either the silos or Baylor is going to be 0.8, which means that they are going to be in the blue or the orange, whatever that is, salmon, or the green. They can be in any one of those three. When we say either, they can be in any one of those three.
Okay, so whenever you have any kind of overlap, you have to use the general.
Yes. When you have any kind, when the events are not mutually exclusive, then you use the general rule. If I use the word or, what's the probability of this or this, and the events are not mutually exclusive, use the general rule.
Okay.
Is that cool?
Yes.
Cool. Okay, in our example up here, we calculated last time the empirical probability and the classical probability. And we determined that in here there are a total of 21 classes, right? So there's one class for low frequency states, and then 2, 3, 4. These are all states that have high frequencies of fast growing companies, right? So how many total classes are there? 21. And then over here, how many total classes are there? 21. Okay, so we're going to come down here, 21. Okay, so there's 21, and so what is the classical probability of this? It's going to be, I'm gonna make that a little bit bigger. What's a classical probability? The classical probability of you being in a low frequency state, of you being in just one of those categories. Why is that? Because the classical probability, remember, is 1, or the number of favorable outcomes, divided by the total number of possible outcomes. How many total possible outcomes are there? 21. There's 21 total possible outcomes. And so because there's 21 total possible outcomes, if I say what's the probability of just one of those outcomes, it's going to be 1 divided by the total number of possible outcomes. You guys tracking with me? Okay, so that's classical probability. And so what's the classical probability of you having a fast-growing company in the state of Texas? 1 out of 21, so equals 1 divided by 21. Okay, so, and then also same thing down here. There's 21 classes. There's a total of 21 possible outcomes. You can be in one of these 21 classes, so equals 1 divided by 21, then equals 1 divided by 21. I kind of did this on purpose just to help you guys keep track of it. It's like, hey, it's just 1 divided by 21 because there's 21 classes and we're only asking for 1 at a time. Okay? Now, what's the empirical probability of this? You come up here and you find the empirical probability. So what's the empirical probability of you being in a low frequency state? What is the empirical probability of you being in a low frequency state? 16.68. And what's the empirical probability of you being, or your fast-growing company being from the state of Texas? 8.15. So you literally just have to copy and paste it. And then what I'd suggest, because these are actually percentages, they're not probabilities. So we are going to go with number. We're going to change it to a number. And I like it going to 3 decimal points. Does that sound good? 3 decimal points. Okay. So now we have the empirical probability and we have the classical probability. Can I do the rule of addition with both of these? What do you guys think?
Yes.
Mm-hmm. Can I do the special rule of addition, or should I do the, what should I do? You're like, what's the question? That's a good question. Now, if I were to say, what is the probability of being from a low frequency state or from Texas, should I use the special rule of addition or should I use the general rule of addition? Special. The reason why it's special is because can I be from Texas and from a low frequency state at the same time? No. So those are mutually exclusive. Okay? Those are mutually exclusive. They cannot happen at the same time. So I would use the special rule of addition to add those up together. Can I, if I were to say my company has a revenue of 20 million to 40 million, or greater than 400 million, should I use, what's the probability of being in one of those 2 categories? Should I use the general rule or the special rule? So if I say, what's the probability of being in one of these 2 categories, of being either between 20 million to 40 million or above 400 million, should I use the special rule or the general rule? You're like, is this a trick question? Can I be in both of these at the same time? That's the question you need to ask yourself. Can I be in both of these at the same time?
No.
No. So I'm going to use the special rule. Okay. Now, what's the probability of me being from Texas or me having a fast-growing company in the state of Texas and it being between 20 million to 40 million? Can both of those happen at the same time? Yes. So therefore, I would use the general rule. Okay. So we're going to come down here. So we've got the rules of addition. You can see the empirical probabilities, so on and so forth. We just did the rule of addition, the special rule. Now we're going to do the rule of multiplication and basically the joint probability. This is actually, this should say general rule addition. But the general rule of addition includes the rule of multiplication, okay? And so when you come down here, you're going to see classical probability, so on and so forth. We're going to skip over this because that's just an example. You don't have all this?
I don't have all of it either.
Oh,
Split it
go.
into different sheets.
Yes. This right here, if you go down to classical and empirical. Oh.
Yeah, ours says like rules of addition.
Oh, so when you jump to rules of multiplication,
Yes.
it catches it up to all this.
There, yep. So yeah, just go on to rules of multiplication. Sorry, I have two different sheets that have basically the exact same thing. It's just where it's spread out. So if you look down at the bottom, see where it says rules of multiplication, it'll catch you up right to where we are.
Okay.
Does that sound good?
Oh,
You feeling better?
yeah.
Sorry about that.
What the heck?
All right. So, let's do this. What is we already determined up here, what is the classical probability of being in a low frequency state? Classical probability of it being in a low frequency state.
Right. 0.0.
Yep, 0.04 something. Okay, so we'll do that. The low frequency state, it's literally, the probability is 1 divided by 21. Sorry, equals 1 divided by 21. And then this one right here, the quantitative, is what's the probability of being between, it should say 20 million to 40 million. I think it's 20 million. Is it 20 million? I don't even know. How many zeros are there? Oh, it is 2 million. 2 million to 4 million. Okay, so what is the classical probability of having a company that has revenue between 2 million to 4 million? What's the classical probability? Anyone? What is the classical probability of having a company between 2 million to 4 million? How many classes are there? 21. So what's the classical probability of 1 out of 21? So equals 1 divided by 21. Okay. And so guess what? This fun little calculator thing here, it automatically tells you, hey, this is the joint probability of being in a low frequency state and between 2 million to 4 million. And then this right here is the probability of being in neither. And then this is the probability of being the probability of any of the outcomes. This is the probability of being in 2 million to 4 million. And then if you come over here and you look right here, this is the probability of only being in a low frequency state. This is the probability of only being between 2 million to 4 million. Okay, are you guys tracking with this? Yes.
Technically, during the test, we could go in this and just input.
I guess theoretically, now that I think about it, yes.
Thank you.
But you got to understand what this is.
Oh, no.
Okay. Yes, this is a calculator that does all the work for you. And that's why down at the bottom, I say, give me your interpretation. Okay. I want you to interpret what you see here. Okay. So if we're going to interpret this, what do we know? You look at this right here, and we see all these different probabilities. Okay. These probabilities mean absolutely nothing unless you know what they mean, right? They're just numbers. So what we're seeing here is we have less than 1%. We literally have like a 0.5% of a probability of being a low frequency state and between 2 to 4 million, right? We have, almost 5% of being 2 to 4 million and almost 5% of being in a low frequency state. Now, what is this? This is classical probability, right? So do you guys think that maybe we should do empirical probability and that would be better information? What do you guys think? Yes, no? Yeah? Let's do some empirical probability. What's the empirical probability of being in a low frequency state? 0.1668, right? So 0.1668 is the probability of being in a low frequency state. And what's the probability of being between 2 million to 4 million?
0.1.
Let's see here. 2 million to 4 million.
8, 7.
Yep, 0.187. So let's come down here and put 0.187. Okay. And so now we can see the joint probability is right here. The probability of being in neither is right there, and the probability of being in all of them together is right there. Okay, why is it always 1?
You're guaranteed to be in something.
Yeah. So right here, you've got the classical probability of everything, and then you go over one more, and this is the empirical probability. So as you go through your worksheet for your project, you're going to be filling in the classical and empirical probability, and then the most important thing, because can it calculate it for you? I think your worksheet, yeah, because it can calculate it for you. Then you've got to interpret it, interpret what it says, interpret what it means. And when we look at this, what's our interpretation? What are we going to conclude about this information?
Based on classical probability, there's a much slimmer chance of falling in one of those categories, but through empirical probability, there's a heightened chance of falling in Texas or a low frequency state and a smaller chance of being in either.
Okay, now, for this right here, I assumed that they were independent events. Okay? Are these probably actually independent events?
No.
No. Okay, and when we get a little bit further, we'll dig a little bit deeper into that, but we're not digging into that right now. But you had a really good interpretation right there that according to classical probability, the probability of it is a lot lower, but according to empirical probability, the probability of any of these outcomes is actually a lot higher, right? These outcomes right here. So in other words, the probability of being in these two is actually higher than the average. Okay, and so give me your interpretation of what it means right down there, and then you'll be solid, you'll be good to go. Okay,